Thank you very much, and thanks to the organizers for this kind invitation. So I want to talk about some joint work with James Martin, who's at Oxford, and also Lauren Williams will present the next talk on some follow-up work in the same direction. So we specifically requested that these talks be one after another so that there'll be some continuity. So I'll maybe repeat some of the things that Olia presented in the last talk, but maybe, well, depending on some of the material, I might skip it or I might actually spend more time on it. So the outline is I want to remind you about the multispecies ASEP first, and which will motivate the question for the model that we study, which is the multispecies push-ASEP. One of our results is something out of equilibrium. So mostly we've been seeing results about the stationary distribution, but we have some results out of equilibrium which are which are sort of new and interesting maybe to this audience. So I'll spend some time on that, and I'll end with some nice formulas for observables. So as always, please feel free to stop me at any time. So the single species ASEP, so as Olia told you, ASEP stands for total asymmetric simple exclusion process. In the single species case, so think about a ring of size L, Z mod LZ, if you like, and you have, N1 particles, and not strictly less than L. And the transitions are that whenever you have a particle followed by a vacancy, they exchange with rate 1. So this is a continuous time Markov process. So each particle carries an exponential clock. Okay, so if I want to define it fully properly, it will take some time, but let's just say each particle carries a 2 exponential clocks with rates 1 and t, so roughly when a particle is followed by a vacancy, they will exchange with rate 1, and if it's the other way around, they will exchange with rate t. And it's a fairly standard result that the stationary distribution of this is uniform. So all configurations of particles and holes will have the same probability, so they're equally likely. It's therefore independent of t. So this is maybe not immediately obvious, but if you think a little, you can prove it. So a natural analog of this is the multispecies ASEP, so where you have several classes of particles, and now you could have several rules, but the simplest one is where they have a hierarchy. So if you want to think in terms of a traffic analogy, you think of the highest species being the fastest car, like a Ferrari maybe, and the slowest species maybe being, my Hyundai or whatever. And there are some empty spots where there's, there's no car in front of it. So as Olia did, we'll index the particle content by a partition, lambda, which has, in general, m sub s particles of species s, and so on, m1 of species 1, and m0 vacancies. So every particle, every site in my lattice will be occupied by something, one of these labels. And oops, sorry, too many buttons. So the multi-species ASEP has the same kind of rates as before. So larger particles will overtake smaller particles to the right with rate 1, and the converse with rate t. So I hope the description is clear. So in this case, the stationary distribution is no longer uniform. So I'll start by describing the situation for t equals 0. Already this is non-trivial. So this is a beautiful theorem of Ferrari and Martin, which Olia also mentioned. So they proved that the stationary distribution of the multispecies TASEP, so this is t equals 0 with content lambda, is an integer divided by this product of binomial coefficients. Okay, so it's really a combinatorial formula, even though they proved it probabilistically. And it's sort of the best thing a combinatorialist can hope for, because for every they not only proved that the stationary distribution, stationary probability is an integer divided by this, they gave a precise combinatorial interpretation. So given a configuration, you can ask, what is this integer that you're going to attribute to this configuration? And that's what I'll describe now.
Question?
Yes?
The definition of the multispecies
yes?
and the requirement provided I larger than j, does that apply to both of the?
Yes. So if I is larger than j, they will exchange this way with rate 1 and the other way with rate t. So,
okay.
Yeah. So larger particles overtake smaller particles to the right. So if you
okay, now
okay.
Thank you.
So if you want to think dynamically, so larger particles tend to go clockwise, and smaller particles tend to be pushed counterclockwise in my convention. Okay, so here is this formula, amazing formula. So this was conjectured by Omer Ingel a few years earlier, and then they proved this. So in particular, this product of binomial coefficients, in the case when you have one particle of each species, is exactly the product of the numbers in Pascal's triangle in the sth row. So it's a really nice sequence. Okay, so let me show you their combinatorial interpretation. Again, there'll be some repetition with what Olia presented. So for example, consider this partition. So what you do is, so there are S is 4 over here. So you construct a discrete cylinder with circumference L, the number of sides, and height S. And on each side, you either put a particle or not. Okay. So and now I have to tell you, so there are some conditions. So for example, there are 2 4s over here. So you choose 2 positions in the first row as particles. So here we chose these 2. In the second row, you choose the total number of 3s and 4s as particles. So in this case, there are 3 of them. So you choose 3 positions to be particles. Then in the next, you choose 5 of them, and in the next, you choose 7 of them. Okay? So you do this uniformly at random. So respecting this particle content on each row. And now we define a projection. So first, we are going to label the particles in the top row. Okay? So we'll label them 4, and we'll project them in row by row as follows. So let's look at this 4. It'll go down and try to find the first available particle on the next row. So this 4 will pick this 4, and then this process continues. So this 4 will look down and to its right and find the first 4. Well, it found one right there, and again it found one right there. So this particle at the bottom row is now labeled a 4. Similarly, we do the same over here. This found the 4 right over there. Then this guy turned right and until it found a 4 at the corner. And then, because we are on a cylinder, the next 4 goes around and wraps and labels this a 4. Is this clear?
So does this depend on the order in which?
Very good question. So I was about to say, so it's not too hard to prove that it does not depend on the order. So it bears a little bit of thinking, but it is true that it does not depend on the order. So the actual path will depend on the order. But, right, so to clarify, the path will depend on the order, but the labeling at the bottom will not depend on the order. Okay? So now we have labeled the particles, we have determined which particles are labeled 4. Now we do the same process with the available particles on the second row. So there's only 1 3, so we call it a 3. Now it will go and try to find the first particle on the right, but it will only look for available particles. So this particle is already labeled a 4, so it cannot pick it. So it will go right and find this one, and then it cannot go below because that's also taken, and so on. So you do the same for the 2s and then the 1s. and the last unlabeled, vacancies are zeros, okay? So their theorem, Ferrari and Martin's theorem, is that you look at all possible configurations on this discrete cylinder respecting this particle in each row, and you find how many of them project to a given configuration. And that is the integer that you were looking for in the previous theorem. Okay, so this particular configuration projects to this this particular whatever multi-line diagram projects to this single configuration. Okay, so that's the content of that theorem. Okay, so Martin later generalized this to the ASEP where you have a T, and in this case you get the same product of binomial coefficients times some T factorials, ratios of products and ratios of T factorials. And here, so just like Olia mentioned, so you are allowed to, so we will construct links between the particles just like before. But earlier, every particle was obliged to link to the first available particle to its right on the next row. But now we are allowed rates of rejection. So this particle may not necessarily connect to this, and we pay a price for that in terms of this parameter t. So if the particle, so we'll assign weights which depend on t. So if a particle has if a particle on the ith row has a particle directly below it, then it's obliged to connect, and then you get a weight 1. Otherwise, every time you skip, you get a power of t divided by some overall normalization. And we'll give what we call a beta weight to a multi-line configuration by taking in each column the number of particles in that column. So that's end product of those. Okay, so let me give you another example. So in this case, this particle which labeled 3, earlier it would have been forced to connect to this one which is currently labeled 2, but if it skips, you get a weight proportional to t to the 1 because it skipped 1, and the denominator is the number of available particles it had to begin with. So it could have chosen this, or this, but it chose the first available one, so you get a weight of t. And similarly, you continue. And the beta weight is just beta 1 to the 1 because there's only one particle in the first column, beta 2 squared, because there are 2 in the second column, and so on. Okay? So for every link now you get a t weight and you get an overall beta weight. Oops, sorry. So, okay, so my slides are a bit off. Okay, so I think I messed up something. Okay, so as Olia mentioned, there's this nice theorem of Contini, De Geer, and Wheeler, which says that the steady state probability can also be interpreted in terms of in McDonald land, where this number that I just mentioned, or this polynomial, can be interpreted as an ASEP polynomial, which Lauren will say more about in the next talk. And the denominator will be the McDonald polynomial evaluated at all ones. In follow-up work, Chen, De Geer, and Wheeler also use this multi-species ASEP to calculate certain duality functions. Okay, so so far we only had weights for the beta weights and the t weights. You can also introduce the q in the McDonald polynomial, and that encodes transitions that wrap around. And they have a more complicated weights for this. So since I don't need it, I'll just give you an example to show you how complicated they can be. And so Cortell, Mandelstam, and Williams proved that this ASEP polynomial in general with all parameters and q and t can be obtained combinatorially as a sum over multi-line diagrams. So in the ASEP world, you're setting all the parameters to be 1. So our question was whether we can find a stochastic process for which you have these more general parameters, betas, and hope possibly with Q and T. So in this talk, I will address this question for Q equal to 1 and T equal to 0. And it turns out that the natural thing you might think of doing does not work. So you could try to say that, particles so if you have some particle A followed by some particle B at site I and I plus 1, you could say that they exchange with rate depending on beta I or some such thing, which explicitly involves these parameters. But that turns out to be the wrong thing to do. And the correct thing to do is to look at a different model, and this is the push-ASEP. Okay? So let me explain the model. So again, we have a ring of size L with, let's say, n1 particles. Suppose you have a particle at site I. Okay? So now the exponential clocks will be on the sites. So each site will carry an exponential clock with rate 1 by beta I. And whenever there's a particle at site I and that clock rings, it will push the particle to its right, assuming there is one, which will push the particle to its right, and so on until it finds a vacancy and it sits there. So this I will go to I plus 1, that will go so on up to j minus 1, assuming all of these are filled, and then at the first vacancy, this move will stop. Okay, so another way of thinking about it is that this particle at site I will, make this non-local move, and it will find the first available vacancy to its right and go and sit over there. So these two are equivalent descriptions. One is a more local point of view, and the other is non-local. Of course, the effect is the same. Okay, so is the model clear? So this is again on the ring. Notice that here, unlike the ASEP, whenever a clock rings and there is a particle, it will move. In the ASEP, certain transitions are forbidden. I mean, if a particle is followed by a particle, in the single species case, then it cannot move. Right? In this case, all moves will, all transitions where there is a particle will, all bell rings at sites where there are particles will necessarily cause moves. So it's a very different dynamics. And also the non-local nature is also something to keep in mind. So here the stationary distribution in the single species case is also very nice. So I recall the elementary symmetric polynomial. Then if you have a configuration of zeros and ones, then the stationary probability is proportional to beta, proportional to the product of the beta i's where there's a particle at site I. Okay? And the denominator, which is the partition function, is simply the elementary symmetric. Notice that if I set all the beta i's to 1, I exactly obtain the uniform distribution with the denominator being n choose L, L choose n1, which is the same as the ASEP. Okay, so again, I can define a multi-species version of this, and this is the multi-species push-ASEP. So this dynamics is going to be a little complicated, but it is natural, as I will explain. So again, you have many kinds of particles which are indexed by lambda, just as before. And let's say the strongest particle is S, and so on. So suppose there's a particle at site I and the bell at site I rings. Okay, so then that particle will move clockwise. It will, because of the second interpretation I told you, we should not think in terms of the push-ASEP. We should think in terms of non-local moves. So the particle at site I will move clockwise. It will find the first weakest particle to its as it moves clockwise, and it will displace it. So it will occupy its location, and the particle that is there will then go and try to find a weaker particle, and so on. and at the end it will find a vacancy and it will sit over there. Okay, so let me explain this with an example.
Vacancy is current 0.
Yeah, vacancy is 0, yeah. So you might think that this is very complicated, but actually it's natural if you think in terms of couplings of single species models. So let me show you with an example. So suppose you are in this configuration. So the initial configuration is the same for these 3 examples. So suppose the bell at the second site rings, then this 4 will find the first weakest particle, which is a 3 right over there, which will in turn find the first weakest particle, which is already a vacancy. So then these 3 will just exchange, form a 3 cycle. So the 4 will go to the 3, 3 will go to the 0, and if it rings at the 4th site, there's already a vacancy, so nothing happens. If it rings at the 5th site, this 2 will go and find the first weakest particle, which is a 1, and that will in turn go clockwise around the ring and displace go and sit at the vacancy. Okay, so this is how they change. So yeah, is that okay, Zach? So yeah, so you can notice that a single move makes a lot of change, and it's highly non-local, right? So things move quite a bit.
And the 1 over beta I, that's the rate?
That's the rate, yes. So the rate was 1 by beta I, yeah.
And it's like site dependent.
It is site dependent, yes. So you lose translation invariance, but you can still salvage it to some extent.
Arvind, is some order preserved, or is everything reshuffled? Like if the colors were 1, 2, 3, 4, if you run these dynamics, will be there any order between these particles which is preserved in the dynamics?
No. So it's ergodic.
So like completely reshuffle.
Yes. So it is ergodic. Maybe it's not immediate, but one can show using some combinatorial argument that. So basically, you can get from any configuration to any other configuration. So nothing is going to be present. So let me tell you about some previous work. So this is an old model. So Spitzer, in his influential paper where he defined the ASEP and the TASEP, also defined a more general version of this, where he was thinking only about single species, when he called this the long-range exclusion process. So he was thinking more in Z or ZD, and then it's not even clear that such a process is well defined. So he had posed it as a conjecture, and that was solved by Liggett. Ferrari and Martin defined this version, a version of this on Z and on R. So they call this the Hammersley-Aldous diaconus process. So there they interchange the role of the particle and the whole. So I can explain more about how this works, but the way they think about it, this allows them to define this process even on continuous spaces like R, not just on the integers. So in previous work with Anna and Ben Steinberg and Nicola Thierry, we had studied a model called the directed sandpile, which we studied on directed trees, where a special case of that is the single species model. And I had, in some follow-up work, studied large deviations for the current for the same model when we look at the open interval. And more recently, Buch and Cox have proposed something which they call the frog model, which is a related multi-species variant. And just 2 days ago, yesterday or 2 days ago, there was a variant of this model by some people, I forget who, which they call frogs with hats. So they have these pictures where.
By the way, it's the same Cox, but changed last name.
Oh, I see. Okay, you have to tell me the story.
I've communicated with them. They have correlated clocks now.
Yeah. Okay. So okay. Anyway, and Agarwal, Nicoletti, and Petrov have studied a more general version that subsumes our version, but their results are different and their techniques are also. Okay, so first to Vadim's question, it is indeed true that the push-ASEP, multi-species push-ASEP is irreducible in general. You can get from any configuration to any other configuration. You don't have translation invariance because of this beta i's, but you have this covariant property. So if you replace I by I plus 1 and simultaneously change beta I to beta I plus 1, mod L, this process is invariant. Okay, so our first result is that the stationary distribution of the multi-species push-ASEP is indeed what we want. It's the ASEP polynomial at q equal to 1 and t equals 0. So with these rates beta 1 up to beta L. So remember that the rates were 1 over beta I. They were not beta I. And this is, I mean, we tuned it so that this works this way. And the denominator is the Macdonald polynomial at q equal to 1, t equals 0, which I remind you is a product of elementary symmetric polynomials. And so in particular, what this says is that if I set all the beta i's to 1, I get the same stationary distribution as the ASEP, which is rather surprising if you think about it. The processes are entirely different, one, as I kept insisting, but somehow you get the same stationary distribution.
Beta I just go up, okay. They're the x variable.
Yes, yes,
okay.
yeah. Okay, so as I said, okay, sorry, I'm just repeating myself. Okay, so here's an example. So if you take the first non-trivial two-species model with 1, 2, 1, 1, and 1, 0, then this is how the transition graph looks like. Somehow Mathematica automatically draws it in this nice symmetric way. The stationary weights are proportional to this, and if you sum them, you get the product of E1 and E2. I'll come back to this in a second. Okay, so how do we prove this? So our strategy is similar to what Ferrari and Martin did. So we will construct a process on this discrete cylinder which I showed you earlier, and we will use this lumping that they also use. So we'll construct a process on the cylinder, and our lumping will be precisely the lumping I showed you earlier, this bully path projection. Okay, so as before, you have mi particles in the ith row, and let me describe the model. Let me describe the process on this cylinder, on this multiline diagram. So again with rate, okay, so maybe I'll first show you the figure. So suppose this is the relevant part of the configuration. Suppose the bell rings at the ith site with rate 1 by beta I. It will make a push-ASEP move. So the ith row will make a push-ASEP move. So it will go single species move. So this guy will hop over there. And now you look to the row above. If there is no particle, you forget that row and you look to the row above it. And so this row has no particle at that site, and so you look above it, and this will find the first, it will make a push-ASEP move. So it will find the first available site to its right. Then you look at the row above, the particle there will find the first available site to its right. So all of these transitions happen instantaneously, okay? So in one time, I mean, whenever the clock rings, potentially particles in each row can move. So with rate 1 by beta I, a lot of these transitions happen at once. And so we also prove that this multi-line push-ASEP is irreducible and satisfies the same covariance properties. And the theorem is that the stationary probability of any multi-line configuration is proportional to beta I product of beta I to the number of particles in column I. Okay. And because of the way we have restricted the configurations in the sense that the number of particles in the ith row, we have some constraint on that. The denominator is therefore the product of the elementary symmetric polynomials, and this is precisely the Macdonald index by lambda. So in this example, there's beta 1 cubed because there are 3 particles in the first row and so on. And the same bully path projection that Ferrari and Martin defined for the ASEP also works here. So the process is different, but the rates are the same. Okay, so let me show you with the same example the stationary distribution. So here we want, let's look at 0 to 1. So we want, so if you think about what's happening on the second row, you have to have particles at these two sides, because otherwise this will not be a 0. And then for the particle on the first row, it can only be in the first or the second side, because otherwise this one will become a 2. So there are two possibilities, and their weights are beta squared beta 3 because there are two particles here and two particles in the second column and one in the third, and here beta 1, beta 2, beta 3. And similarly for the other, and if I go back to this example, you see that 0 to 1 was the sum over here. Okay. So it all works out very nicely. Okay, so how much time do I have, Anna?
20 minutes.
Okay. So I can spend some time on interchangeability. Oh, sorry, that's a typo. There should be an R there. Okay. So so in queuing theory, there's this beautiful theorem called Weber's theorem. So I think, yeah, okay. So let me tell you what it is. So probabilists study these queuing processes where you imagine, like a bank or somewhere. There's a queue of people formed who's served by a teller or whatever. And so there's a process for, there's a distribution for the number of people waiting in the queue, and there's a rate at which they are served. So there are these two distributions, and the result is the output distribution. So in this notation, this means that, so there are two queues, A and B, where the incoming, the arrival process is arbitrary. There's absolutely no constraint on that. The service is Markovian, M stands for Markovian, and there's only one server. So, and we are considering two tandem queues. So tandem queues means when one person is served by the first queue, he or she immediately joins the next queue. So you might think that's ridiculous. Why would you do such a thing? But just this weekend, my flight got cancelled, and I had to go. So I had to get my flight rebooked on Lufthansa. So I had a queue to join the Lufthansa service center, and immediately I had to join the queue to go to an agent. So it was it's a perfect example of a tandem queue. So. Okay, so suppose there are two tandem queues which are served by different rates, at different rates mu1 and mu2. So they're Markovian, so they're exponentially served. So Weber proved that if you interchange mu1 and mu2, the output, the departure process is the same. So imagine, so if you want to think dynamically, suppose mu1 is very large and mu2 is very small. So you are quickly passed to the next queue like I was, but the other one is slow, so you sort of come out slow. But imagine it were the other way around. Then to pass through the first queue would take a lot of time, but you would leave quickly once you got to the second queue. So intuitively it's not, I mean, it seems okay, but the fact that this holds is non-trivial. I mean, there is something to prove, okay? So this is an example of an interchangeability theorem. And so there were several proofs, and in particular, there's a coupling proof that by Tsukas and Wallerand, which we will use. So our result is the following. So so this is a genuinely non-equilibrium result, okay? So we are not saying, we are not in stationarity. You start the process, and at any finite time, the following result will hold. So you start the multispecies push-ASEP either in the stationary distribution, or for some fixed k, you fix the configuration in the last k plus 1 L minus k sides, sites k plus 1 through L, which are weakly decreasing. Okay, so that's some technical constraint that we need. Then the statement is that anything that you look in the first k sites, absolutely any observable that you look at any time is going to be invariant under the permutation, any permutation of the last k plus 1, last L minus k sites. Okay, so just to give you an example, so here is site k plus 1 through L. So here initially you want something going over here is greater than or equal to here. So what we are saying is that if you just look at these sites 1 through k, you don't focus on the remaining. At any point of time, even before you reach stationarity, whatever you observe, whatever distribution you observe here will be invariant under any permutation of these rates. Okay, so this is an example of an interchangeability theorem. So the actual choice of the, I could order these beta k's plus 1 through beta L in decreasing order or increasing order. Whatever I do, I'll get the same thing. Okay? And the result is already non-trivial when you have a single species. You have only zeros and ones. So what this is, so let me interpret this for you in this context. So suppose you have two systems you're running in parallel where all you do, so the initial configuration is the same. All you do is interchange two adjacent rates, okay, beta j and beta j plus 1. So here it's j plus 1, here's j plus 1j, okay? And you run the two systems. And we insist that the initially the configuration at these two sites is either of the form 0, 0, 1, 0, or 1, 1. We do not allow 0, 1 because that will muck up the proof. It will not be true. So then if I look at any other site other than these two, then the distribution of the process will remain the same. Okay? Doesn't seem obvious at all. So to prove this, we need the flux process. So this just records whenever a particle passes through two sites, two adjacent sites. So j plus 1. Okay, so I'm looking at this bond and I'm seeing whenever a particle passes from here across this bond. So it could go like so, it could go like so, whatever, you know. So or it could just go from j to j plus 1, it doesn't matter. It has to cross that bond, okay? So now it's not hard to see that if you know the flux process at j minus 1j, and you know the occupancy at j at time 0, and you know the sequence of bell rings at j, then you get the flux process at the next site. So you're able to determine the process of transfer of particles between two adjacent sites from one to the other. So you can pass information from left to right. And so the lemma is that there's an explicit coupling. So think of the, okay, so let me go through this carefully. So you think of the flux process between sites j plus 1 and j plus 2 as a function of the left flux process. So the R stands for right, L for left. The flux process between j minus 1 and j, the processes of bell rings at sites j and j plus 1, and these configuration at these two sites. So then we can construct an explicit coupling between this product of some processes such that the flux process on the right has the same distribution independent of whether you looked at beta j plus 1 or the other way around. Okay, so somehow, so what happens in the middle you don't know, but once you cross that, you'll get the same distribution. And so this is a pictorial representation of the theorem. So PP stands for Poisson process. And the proof idea is an explicit coupling where if I have the bells ringing at site j and j plus 1, we know that I take the union of these. This is also a Poisson process, which we call A plus B, and then there's a natural way to break them into A tilde and B tilde, such that the beta j and the beta j plus 1 are switched. Okay, so that's the key idea, but there are a lot of technical details. Okay, so in the last 5 minutes, I want to spend some time on correlations. So usually physicists are interested not in the full stationary distribution, but at specific observables. And the two most important observables are according to me at least, are the current and the density. So because this is not an equilibrium process, this is in the sense that detailed balance does not hold. There is a flux of current. There's a flux of particles across any bond. So that is, roughly speaking, the current. And the density is simply the occupation probability. So both of these observables can be computed explicitly, for the multi-species case, just by looking at single species case because of the way the process was constructed as a coupling. Okay, and somehow, for some not completely well understood reason, the Schur polynomials seem to figure in all these formulas. We don't know why. Well, we know why because of the way the proof works. In all these cases, the Jacobi-Trudi identity seems to be needed, but at some philosophical level, why Schur polynomials are entering is not completely clear. Okay, so let me define the current. So remember we have multiple species of particles. So we have conservation of each of these species. So we can ask. So I look at a bond, and I see how many particles of type J cross that bond in unit time. Okay, in the long time limit. So I can essentially do this computation in the stationary distribution, and because the particles are conserved, it does not matter which edge I look at. So I can look at any pair of consecutive sites and the edge between them. And so it turns out that sorry, this is a typo, it should be push-ASEP. The current for the multi-species, for the species J in the multi-species push-ASEP is a Schur polynomial with certain number of 2's and 1's divided by a product of, divided by a certain elementary symmetric polynomial. Okay, so the proof is not difficult. One just has to compute the current of two single species push-ASEPs and take their difference. And the density of a particle of species J is simply the probability that there is a J at a certain site. And because of this covariance that I told you about, it's enough to calculate this at the first site. And in this case, we obtain up to a factor of beta 1, a Schur polynomial in the other L-1 variables, again divided by an elementary symmetric polynomial. So by this interchangeability theorem, we know that this will be a function only of, this will be a symmetric polynomial in beta 2 up to beta L. And it turns out to be a Schur polynomial. Not symmetric in beta 1 because it's over there. And the last result is a bit harder, and this is the 2-point nearest neighbor correlation. So now so earlier I was only asking for the density, which is at one side, but I can ask for two consecutive sites. And you might wonder, well, why should I go about this? And I'll give you a motivation in a second. But just to finish the story, the formula, so I define these two complicated functions, fji and gji, which again depend on Schur polynomials. And I only do this calculation when there's one particle of each type. And in this case, we get sort of explicit formulas for the probability that there's a species J at site 1 and species I at site 2. Of course, because we have one of each kind, it's 0 when J equals I, because they cannot be more than one of the same species. But in all other cases, we have some explicit formula. And so when J is less than I, it depends on this function f divided by this elementary symmetric polynomial. If J is greater than I, there are two cases. When J equals I plus 1 is somehow special, and otherwise you get this dependence on G. And why would you care? So this generalizes a formula that I had obtained jointly with Svante Linnaeus, where we use this to prove a certain conjecture of Thomas Lamb. On a certain random walk he had constructed on the affine Coxeter arrangement, and his question was about the limiting direction, and we were able to use this two-point computation. So this suggests that there's a more general formula, a more general random walk on this Coxeter arrangement, which has not been studied. And if we let L go to infinity, then there is this TushTASEP. It generalizes a formula of Amir, Angel, and Valco on this TushTASEP speed process for correlations in the TushTASEP speed process. So we felt it was kind of natural to study this generalization. Okay, that's it. With that, I'll thank you for your attention.